Okay, well, this is actually going to be an application of constructor theory to this problem of information that we've been discussing and sort of touching upon during the previous talks. So like information is a bit like a sort of a placeholder for a rich undergrowth of problems in physics. At least this is what is the impression that we've gathered in these days. And but I think the root of the problem is that there's a sense in which information appears to be fundamental in physics, or at least there are hints to this fact. For instance, we have laws about information which are expressed in quantum theory computation, for instance, laws about channel capacity, which do not refer to physical substrates, but are about this entity which we call information. And similarly, there are laws such as the Bekenstein formula for the entropy of a black hole, which seem to link this notion of information to fundamental quantities in nature. And also, information is of the essence, like in preparation and measurement. But on the other hand, I mean, on the face of it, it doesn't look like it's not an observable. It doesn't look like a function of tensor fields of space-time. And as I said, its notion is substrate independent, so it doesn't depend on the physical systems that instantiate it. So I think we should sort of ask what does it mean to have a physical theory, a fundamental physical theory of information? Okay, so here's one first thought. Whatever that means, it can't be Shannon's theory. And yesterday, Philip mentioned Shannon's theory briefly. The reason is that Shannon's theory, well, apart from the fact that it's formulated in a classical context, but it conceals a circularity at its foundation. And the reason is this. So Shannon considers the situation where there's he's proposing analysis of the physics of communication. So there's a source, a receiver, and a medium through which messages are sent. And the problem he's interested in is, in fact, not investigating the foundations of information, but if you look at his setting from this foundational point of view, you see that there is, as I said, there's this tower of Tartus, precisely because he doesn't consider, he considers a classical setting. He didn't have to model explicitly the process of distinguishing messages, which is at the base of the process of receiving those messages. And if you look more closely, of course this is because different states in classical physics are distinguishable. And if you try to see and come, to find a definition of what it means to be distinguishable, then in Shannon's scheme, in Shannon's setting, there's no room for giving a satisfactory answer. Because you could say the two states are distinguishable if a process of this kind is possible, where these two states, S of x and S of y, are distinguishable in turn. And this is a recursive definition of distinguishability. And if you don't provide a base, physical base for it, this is a circularity. So I'm suggesting that there is a problem at the foundations of Shannon's theory. We can't express what it means to be distinguishable, because distinguishable in turn relies on distinguishability, or, if you like, on information. So, yes?
Would you mind repeating what the zeros and the s?
Yes, so these are states. So x and y are states or attributes, more generally, of the system. And 0 is a blank state, that's a receptive blank state. And I'm proposing, this is an operational criterion, which is the one would like to look into when it's trying to define what it means for two states to be distinguishable. And in Shannon's approach, there's no room for providing a base for this recursion that this definition hints to. So that's my point. Does that make sense? I mean, the setting is clear? Thanks. Okay. So now, the reason why this wasn't, the reason why this problem doesn't immediately, is not immediately noticed, is that we are accustomed to thinking about information as an a priori concept. So we find it plausible to consider that as an a priori concept. And in fact, Wheeler, when he suggested the view of it from bit, was assuming that these bits were the primitive concepts in terms of which the reality, could be explained. But we would like to suggest that these bits are in fact rooted in physics, and so this is how we conceive this notion of information being rooted in physics. I'll give you a counterexample to this idea that information is an a priori concept. Consider laws of physics, where we had two worlds, world A and world B, and suppose world A were just like ours, except that, so in other words, we could have computation, information, measurement, science, and so would be world B. But they couldn't communicate. So the interactions of this putative world that we are considering was such that world A and world B were not capable of interacting one with another. And that would mean that we couldn't have this property that we usually associate with information, that is that it can be copied from any medium to any other. This is something that we don't really acknowledge when we talk about information, but it's a deep assumption. I mean, it's actually a non-trivial statement about what the laws of physics that rule the world that we're talking about are. And so this is the sense in which information is physical. So whenever we talk about information, we are referring to regularities in nature. And we currently don't have a theory of these regularities. And so the proposal that David and I are sort of developing at the moment is that a theory of information, a fundamental theory of information in physics should be about expressing these regularities. And of course, precisely because of this substrate independence that I mentioned before, this theory must be at a deeper level than quantum theory or general relativity or the most fundamental theories that we have at the moment. And we're guessing that this theory might be constructor theory. So that's the problem that we're trying to address. So we're trying to express these regularities which are required for laws of physics to be capable of instantiating information. And we would like to do this by using constructor theory. I hope this is, I was just trying to explain the problem situation. I hope this is a clear explanation of it. And now I'll outline the logic of the solution. So I won't go into the details, but I'll express the logic of the construction that we're proposing. Okay, so constructor theory. Is a first of all, it is a physical theory in which every current physical theory can be expressed. And in fact, so if we have quantum theory and general relativity, constructor theory underlies these two and others which one could conceive. And the basic principle of constructor theory is that every statement about laws of physics must be expressed in terms of statements about what tasks are possible and what tasks are impossible and why. And this is a departure from the prevailing conception of fundamental physics in which you use initial conditions and laws of motion, which can only describe the actual, that is, what happens. But in constructor theory, we also accommodate for a description of what can happen and what cannot happen. So we have more room to express statements. And when I talk about tasks, I think of describing physical processes as transformations, where there's a subsystem which is called the constructor, which is what causes the transformation to occur under the given law of physics, which could be a unitary or could be any other dynamical law that you could think of. And the other subsystem is a substrate, which is what is changed by the constructor. And the constructor is distinguished by the fact that under this law of motion, it remains unchanged in its ability to cause a transformation again. And note that there's no, it is an objective description and there's no observer involved in this. We're not thinking of the constructor as being a sentient being or anything like that. It could be a fridge, it could be a catalyst, and that is, so that's what I mean by transformation. And the task is the specification of the change that the substrate undergoes. So the task is a specification of the change in terms of all the pairs of attributes, like initial and final attributes you can conceive of. I mean, it's expressed of a set of ordered pairs of such input-output attributes or states. Yes?
Constraints on the tasks.
Oh, yes. So you mean possible and impossible? Yeah. Yes. So these theories, which are called subsidiary theories, can be translated into constructor theory, and they provide the statements about what tasks are possible and what tasks are impossible. But that's the thing that I was about to say. Constructor theory is not just a language in which you translate things, but it has principles. So it constrains these other theories. And some of these might not be compatible with the principles of constructor theory. So I won't go into the details of these. I'm happy to answer questions afterwards. But it's just to say it's not a contentless framework. It has non-trivial statements such as composition of two possible tasks must be a possible task. And such as the principles of information, about information that I'm going to discuss in a moment. Okay, so let's see how we can address the problem that I mentioned before by this new take of formulating science in terms of tasks instead of in terms of initial conditions and laws of motion. Okay, I'll describe the logic of the construction. So we start by defining computation media. So computation media, let me represent them, this is a set of computation media. So they are substrates on which have at least one set of states that can be permuted in all possible ways. So the interactions, the laws of physics are such that all possible permutations of these, the states of these media are possible. So, for instance, a qubit would qualify as a computation medium with, say, the set of states plus and zero. I'm talking to the quantum information people in the audience. These are two non-orthogonal states, non-distinguishable states, which can be permuted. And so this suggests that the notion of computation comes prior to the notion of information, at least in our description. So we are, and this is actually the way we cure the circularity that I described before. And also, computations don't require an observer to be around. So, yes?
So why are you choosing non-orthogonal states?
I'm sorry, say
Why
again?
are you choosing non-orthogonal states?
Oh, it's just an example to illustrate that we are not requiring computation media to have distinguishable states in the sense that you usually use in quantum information. This is might be a counter, I mean, it's not the usual take, so I just picked this example to make clear to, to sort of guide the interpretation of what I'm saying.
And what would it mean to permute the state?
Oh, it would mean to,
Oh, I see.
have an operation that performs this and the identity, the unit transformation. So all possible permutations of this set. So then we look at a subset of these, which are information media, which are computation media, which have therefore an information variable, one that can be permuted in all possible ways, but also satisfy an additional constraint. That is, if you have two of them, two replicas of the same system, the information variable of one subsystem can be copied on the other subsystem and vice versa. So that is, we require additional interruptions to be available. For instance, we require a process of this kind to be possible, where 0 and 1 is the computation variable that I'm considering. So this is an additional requirement, an additional task that we require to be possible for information media, which distinguishes them from computation media. And therefore, this one wouldn't be considered as an information set anymore, though it's a computation set. Now, note that this is all defined in terms of what is possible and impossible, which is an objective concept given by the laws of physics. And this is precisely the reason why we can cure the recursion the circularity that I mentioned before, because now we can define distinguishable sets, or sets of states or sets of attributes by using information media. And so a distinguishable set of attributes is one for which a task of this kind is possible, where every state of the set that we are defining to be distinguishable, according to the laws of physics, can be mapped onto this other state, where these are states of another subsystem, a receptive subsystem, which is an information medium. And what these should be is defined in terms of possible and impossible, and this cures the circularity that was presented before. Yes?
There's a question of clarification. The states,
Yes.
like 0 and plus,
Yes.
they are examples of attributes of systems.
Yeah, I'm being very sloppy in my terminology. I should talk about attributes. And
But they are examples of attributes.
yes, they are examples of attributes. Attributes are sets of states, and some attributes, precisely information attributes, are pure and mixed states, which are in the +1 eigenspace of projectors, of a given projector, which could be any rank. So, so you might think of those as being, as information attributes are these kind of things. Okay, so now there's an additional point in our construction that is that we define a subclass of information media, which we call supercomputation media. And before doing that, we give a set of principles about information media, which are these proposed laws of nature that I was referring to before. And so I won't give these laws, but I would like to say that these laws are expressed in exact terms. They have an elegant expression in terms of possible and impossible tasks, and they are about information only. So they capture this notion of information, and they find a natural expression in terms of, as I said, tasks. And this is an example. This property of being capable of copying information from one medium to another finds this elegant expression that is the interoperability principle. That is that the combination of two information media with variables, each with variable S1 and S2, is an information medium with an information variable that's the Cartesian product of the two. And if you consider what that means, it means that all permutations on this set must be possible, in particular, and the set of permutations on this set includes the operations that correspond to copy of S1 onto medium 2 and of S2 onto medium 1. So, and this is not a consequence of the definitions. You might come up with some model which doesn't satisfy this, but we are conjecturing that there's a principle which has this form and which expresses precisely the property that I mentioned before. That is that we assume that information is interoperable and can be copied from one medium to another without paying attention to the fine details of these media. I'm happy to discuss the principle afterwards, but I wanted to complete the description of the logic of the construction because that's what I would like to describe today. Okay, so superinformation. So superinformation is here. I should use another color, but so these are superinformation media. So superinformation media are information media which have at least two variables, two information variables, so two sets that can be permuted and copied, but have an additional constraint, which is that if you consider the union of these two variables, what you get is not an information variable. So again, if we consider an example with qubits, you might consider a qubit as being a superinformation medium with sets 0, 1, and plus, minus. And if you consider the union of these two, although each one is an information variable, the union of these two variables is not an information variable because, in particular, you can't copy the whole of the union. So it's so this is a very simple constraint that we are imposing. And note that we haven't talked about probabilities so far, and the notion of possible and impossible is an exact one. And it's very, so what we do at the moment, what we do after defining superinformation media this way, is to prove that they satisfy the properties that I've listed here. Now, each of these terms has an expression in constructor theory, which requires explanation. This is just a list, and as I said, I'm very happy to discuss this later. So we prove that these media display the feature of having pairs of states that are not distinguishable and not clonable, They display the effect, like the reducible perturbation caused by measurement. They also display unpredictability of outcomes of measurement. And with an additional constraint of reversibility, we can show that if we consider the composite medium of two superinformation media, such a medium displays locally inaccessible information. Now, all these terms must be explained, and they have a non-trivial expression in constructor theory. But what I would like you to see from this list is that they're all concepts which are defined within the theory that we've constructed, and they don't rely on any other axiom or principle except the ones that we defined about, that we proposed about information. So these are among the most distinctive properties of quantum media, and we have constructed them inside the theory of information media. Yes?
So could you briefly say how you talk about measurement within this?
Yes, so measurement is a task which is quite similar to the task of distinguishing states, I should say. So measurement is, I mean, you could talk about perfect measurement. This is an imperfect, so measurement is basically a task of this kind. So a measure is a constructor for this task, for the task of, and we say that the set X is a measurable set. So a measure is a constructor for a task. A measure of X is a constructor for a task of this form. So that's how we model measurement. And I think it's very beautiful that from a simple constraint, that is this constraint about the union of two information variables not being an information variable, which is very elegant in constructor theory, we can recover this structure. So that's, I think that's the end of my talk, in the sense that, that's what I wanted to describe. I wanted to describe the logic of our construction and our results. And I'd like to comment on certain things. The first is, as I said, I didn't mention probabilities in this setting. So this suggests that probabilities don't play a role to a fundamental definition of information. I haven't mentioned observers, and this switching to formulating science in terms of tasks is a way to get around the problems that we talked about yesterday with Owen, that would seem to hint to the fact that information depends on the existence of an observer. But in fact, what information is about is the presence of certain interactions in physics, and that's expressed in an objective way. And that's what we've done here. And then I would also like to say that the fact, why are we interested in constructing this theory about superinformation media within information media, and how is that different from, say, trying to axiomatize quantum theory? So we would like to be able to answer questions of the form, could we have some laws of nature under which quantum information processing is possible, which are different from quantum theory? And if you think of this question and you ponder, you consider what quantum information theory is at the moment, you see that we can't quite answer this question within quantum information theory. Because quantum information theory is a sort of hybrid between concepts that are borrowed from information theory, the classical version of it, and quantum theory. And so it's sort of tied to quantum theory, and therefore if you want to ask questions which underlie quantum theory, which consider different theories from quantum theory, you can't do that within quantum information theory alone. But in this framework you can, or that's a sort of the kind of framework that you need in order to address these problems. Okay, so I'll conclude by a nice quote by Eddington, which actually is quoted by Fisher and then later by Dawkins. So it's a quote that appears to be a replicator in some sense because, it's interestingly constructor theoretical in flavor, because it says that we need scarcely add that the contemplation in natural science of a wider domain than the actual leads to a far better understanding of the actual. And if you think of this as being the actual, or is what the prevailing conception of physics can capture, and well, we hope that constructor theory can in fact contemplate